Hi everybody, in this video we are going to go over section 3 of chapter 3, zeros of a polynomial function. In this section we are going to discuss the factor theorem, the rational zero theorem, the fundamental theorem of algebra, the conjugate zeros theorem, and we're going to talk about zeros of a polynomial function for the cases where the polynomial is of even or odd degree, and then we're going to talk about Descartes' rule of signs. And we will get started with the factor theorem. And this is what it says. For any polynomial function, we're going to call it f, x of k is a factor of f if and only if f evaluated at k is equal to 0. So this pretty much tells you two things. The first thing it tells you is that if f evaluated at k is equal to 0, well then that implies that f of x is or that x minus k is a factor of f, which means you can write f of x as x minus k, or the product of x minus k, times some other polynomial, and of course that'll be equal to f. Furthermore, if x minus k is a factor of f, which means that this is true, let me put the x over here as well, then that implies that f evaluated at k is equal to 0. So what does this give you? Well, basically this gives you two ways to determine if x minus k is a factor of f, which might be useful for factoring your polynomials. It also gives you two different ways to determine if k is or is not a zero of f. And how can we put this to use? Well, take a look at our very first example. Here we want to determine whether x minus 1 is a factor of f. Well, there's two ways you can do that. First thing is you can substitute 1 in for x, and if you do, you're going to have f of 1, and that is equal to 2 times 1 to the 4th plus 3 times 1 squared minus 6 times 1 plus 7 times 1, which will be equal to 6. The other way, if you wanted to do it this way, this might be a little more involved, is to compute f of x divided by x minus 1. There's try to divide out x minus 1 and see if you actually get a quotient with no remainder. And of course we can use synthetic division to do that. We can put our coefficients down, which would be 2 for the quartic term. We have no cubic term, so we're going to put a 0 here. 3 for the quadratic term, negative 6 for the linear term, and then 1 for the for the constant term. And of course our divisor is going to be x minus 1, so we're just going to put a 1 here. We can bring our 2 down and go ahead and do the math. 1 times 2 is 2. 0 plus 2 is 2. 1 times 2 is 3. No, 1 times 2 is 2. 2 plus 3 is 5. 1 times 5 is 6 minus negative 6 plus 5 is negative 1. 1 times negative 1 is negative 1. And we get 6, which is what we get here, which would make sense, which is consistent with the remainder theorem. Okay, so here, once again, we have two ways. The factor theorem gives us two ways to determine whether or not this is a factor of, whether or not x minus 1 is a factor of f. Accordingly, the factor theorem gives us two ways to determine whether or not x plus 9 is a factor of f. The first one way is to evaluate f of negative 9. Of course, to do that, we would need to know what negative 9 to the 5th is, what negative 9 to the 4th is, and those are pretty big numbers, and there's a lot of algebra here that can go wrong. So in this case, another way you can do that is to use synthetic division. Not only will you determine, and the best part about synthetic division is not only will you determine if this is a factor, if it is indeed a factor, you will also figure out what the quotient is. And you might be able to use that if you have more factoring to do, which we will have later in this section. So let's go ahead and work this one out. Here we are going to have our coefficients are 3 for the quintic term, negative 6 for the quartic term, negative 246 for the cubic term, plus 492 for the quadratic term, 423 for the linear term, and then negative 486 for the constant term. And we're going to divide, and then we are going to divide all of this by x plus 9, so we're going to put a negative 9 here. Okay, so we can draw our line down here. We can bring our 3 down, and we have negative 9 times 3 is negative 27. And this will add to negative 33. Negative 9 times negative 33 is positive 297. Okay, and then we do the addition here, we will have a positive 51. Negative 9 times 51 is going to be negative 459. Adding 492 to negative 459 will give us positive 33. Well, we've done that one before, except now we have a negative 9 and positive 33, so that will give us a negative 297. And then when we add these, we will have negative 54. And conveniently, negative 9 times negative 54 is positive 486. So we get a remainder of 0. So it turns out that this is indeed a factor of g of x. Okay, I should have had g of x instead of f there. On top of that, we also know what the quotient is. This right here is the quotient. Okay, and here is one more example. Now we want to factor f of x equals 6x cubed plus 19x squared plus 2x minus 3 into linear factors, giving that negative 3 is a 0. Okay, well, according to the factor theorem, if negative 3 is a 0, and we're being told that it is, then that means that x plus 3 is going to be a factor of f. And that means we can actually divide f of x by x plus 3, and we will get a quotient. So let's go ahead and do that and figure out what that is. Here we're going to do, once again, use synthetic division. Our coefficients are 6 for the cubic term, 19 for the quadratic term, 2 for the linear term, and negative 3 for the constant term. We're going to divide all of that by negative 3. Bring the 6 down, and let's go ahead and do the math. Negative 3 times 6 is negative 18. Okay, 19 minus 18 is 1. Negative 3 times 1 is negative 3. 2 minus 3 is negative 1. Negative 3 times 3 is 3, as we would hope, or there is a problem. And of course, our remainder is 0. Once again, these are the coefficients for our quotient. So our quotient is going to be 6x squared plus x minus 1. Now, this we can actually factor, or if we couldn't factor, maybe we could actually find the zeros, or we could actually use the quadratic equation, or the quadratic formula as a tool to factor this. But this we can actually factor. We need to find factors of 6 that will sum to 1. Okay, so in this particular case, what we would need is perhaps 3x minus 1 times 2x plus 1. Does that work? Of course, 3x times 2x is 6x. 3 times 1 is 3, minus 2 times, or 3x times 1 is 3x, minus 2x times 1, which is minus 2x. They subtract out to give you your positive 1, and negative 1 times plus 1 is negative 1. So this indeed works out. So these are the other two linear factors. As a consequence, we can write f of x as follows. The factor associated with the 0 of negative 3, which will be x plus 3, times 3x minus 1, times 2x plus 1. And there you go. Now, this brings us to the rational zeros theorem. And what is so great about this theorem? Well, let's suppose that you actually have a polynomial and you have no idea what the zeros might be. This will give you a list of candidates for zeros. And this is pretty much how it works. Suppose that we have a function of f of x, and suppose it has integer coefficients. Further, suppose that the ratio p over q is a rational number written in lowest terms, which basically means the only factors that p and q share is 1. And suppose that it's a 0 of f. Then p is a factor of the constant term, and q is a factor of the leading coefficient. So if you actually had a function f of x that looked like this, a(n) times x to the nth power plus a to the n minus 1 times x to the n minus 1 all the way down to plus a sub 1 x and then plus a sub 0. This tells you that p is a factor of a sub 0. P is going to be, p is a factor of a sub 0, which basically means that a sub 0 is going to be equal to some number, some integer, times p. And it also tells you that q is a factor of the leading coefficient, which basically tells you that the leading coefficient, in this case a sub n, is going to be equal to some number m times q. And one or more of the ratio of p to q be a zero of f. So how does this work? Well, with this information, we can find factors of a sub 0 and factors of a sub n. We can look at all the possible ratios and evaluate each one using trial by error to see which one is a 0. Once we have found one or possibly two, we can use the rest to completely factor the equation. So how the heck is this going to work? Well, let's find out with this particular example. Here we have the following polynomial function. It is 8x to the fourth minus 26x cubed. Well, you can read it. It's right there. So the leading coefficient here is 8. The factors of 8 are, well, plus or minus 1, plus or minus 8, because 1 times 8 is 8, or negative 1 times 8 is 8. And then there's plus or minus 2 and plus or minus 4. These right here are our candidates for Q. Now our constant term is 4, and the factors of 4 are, well, plus or minus 1 and plus or minus 4. And then there is basically plus or minus 2. Now, what are all the possible zeros? Well, all the possible zeros are all the possible ratios of p to q that you can find with these factors. Let's start off with p being equal to 1 and then vary q to write down all the factors. So we're going to set p equal to 1. Okay? Well, actually, let's set it equal to plus or minus 1. Okay, so that's one possible zero. The other possible zero is going to be is going to be plus or minus 1 over plus or minus 2, which will give us plus or minus 1/2. Then plus or minus 1 over plus or minus 4, which will give us plus or minus 1/4. And then plus or minus 1 over plus or minus 8, which will give us plus or minus 1/8. Okay, so that's basically all of the ones that we have. Now let's go over to this one, which is 2. All right, so now p is going to be 2, and we're going to look at all the values for q. Okay, for this particular case, we are going to have plus or minus 2 divided by plus or minus 1. That's going to be plus or minus 2. Then plus or minus 2 divided by plus or minus 2, that's plus or minus 1. We already have that, so we don't need to write it down. And then finally, plus or minus 2 divided by plus or minus 4. Again, all possible ratios. Well, that's just plus or minus 1/2. And we already have that. So that takes care of 1 and 4. Now we're going to look at all the possible ratios of p and q where p happens to be equal to 4. Okay? So that's plus or minus 4 divided by plus or minus 1, which is plus or minus 4. All right? Plus or minus 4 divided by plus or minus 2, which is plus or minus 2, which we already have. Plus or minus 4 divided by plus or minus 4, which is plus or minus 1, which we already have, and then plus or minus 4 divided by plus or minus 8, which is plus or minus 1/2, which we already have right over there. So these are all the potential rational zeros for this particular polynomial. And then step 2 is, well, not final, but find. That was interesting. I better make sure I fix that before class. Find all rational zeros and factor f of x into linear factors. Now to do this, I'm going to go over to OneNote where I have more space to work. Here I am in OneNote. Here is a screenshot of the equation of the polynomial, and here are my possible zeros. So at this particular point, we have to do trial by error. So let's go ahead and pick a potential zero. How about x is equal to 1? Okay, we're going to see if 1 is a potential zero. And then what we can do is we can either evaluate f of 1, or what we can do is do synthetic division. Now, evaluating f of 1 in this particular case would be easy, but if it turned out that f of 1 was a 0, after if we evaluate this and we turned out that f of 1 was a 0, then we would have to go and do synthetic division anyways to find out what the quotient is. So it might be better just to go ahead and do synthetic division. So let's go ahead and do that. We're going to have 8 for our quartic term, negative 26 for our cubic term, negative 27 for our quadratic term, 11 for your linear term, and 4 for your constant term, and we are dividing all of this by 1. And remember, if 1 is a factor, if 1 is a 0, then x minus 1 is a factor. So let me draw my line. Here's my negative 8, and let's go ahead. No, positive 8. What was I thinking? Positive 8. Here we go, positive 8. Okay, so 1 times 8 is, well, 8. 8 minus 26 is negative 18. 8 minus 26 is negative 18. Negative 18 times 1 is, well, yeah, negative 18. Negative 27 plus negative 18 is negative 45. Negative 45 plus times 1 is, well, yeah, negative 45. Love these easy, hard multiplication problems. Negative 45 plus 11 is negative 34. Then times 1 is still negative 34. And then we add these together, we get negative 30. So turns out that that x equals 1 is not a potential 0. Okay, let's take a look at x equals to negative 1. In this case, we're going to do the exact same thing, except we're going to replace our 1 here with a negative 1. So we have negative 1, 8, negative 26, negative 27, 11, and 4. Okay, so here's my line. Bring down my 8. Negative 1 times 8 is negative 8. Negative 26 minus 8 is negative 34. Negative 1 times negative 34 is positive 34. It's getting ahead of myself there. Negative 27 plus 34 is positive 7. Negative 1 times 7 is negative 7. 11 minus 7 is 4. Times negative 1 is negative 4. So it turns out that x minus 1 is a 0. So basically this will factor into x minus 1, no, I'm sorry, x plus 1. If negative 1 is a 0, then x plus 1 is the factor, times a quotient. And that quotient is going to be 0, 1, 2, 3, 8x cubed minus 34x squared plus 7x plus 4. Okay? So now we need to find 3 other factors. Given the fact that we have a 4 here, there will be 4 factors. So we found one of them, we have to find the other 3. Now, once again, we can do trial by error on this reduced, on this particular factor and see which one is a factor of this particular factor. If it's a factor of this factor, then obviously it's going to be a factor of f. Now, my advice in this particular case would probably to look at the integer values. And of course, I don't think you guys want to see me spending the entire day doing trial by error. So how about, just for kicks, we try x equals to 4. Okay, so let's set up our synthetic division with x is equal to 4. For the cubic term, we have 8. For the quadratic term, we have negative 34. For the linear term, we have 7. And then for the constant term, we have 4. We are dividing by 4. Or actually, we're dividing by x minus 4, so it's going to be a positive 4 there. Draw my line, bring my 8 down, and let's go to town. 4 times 8 is positive 32. Negative 34 plus 32 is negative 2. 4 times 2 is 4 times negative 2 is negative 8. 7 minus 8 is negative 1. 4 times negative 1 is negative 4, which gives me a 0. Okay, so that tells me that x minus 4 is going to be a factor. So I can put an x minus 4 up here. And the quotient to those two factors is going to be, I'm going to just call it q tilde of x just for kicks. And that's going to be equal to, ignore that 8 squared minus 2x, 8x squared minus 2x minus 1. And this we can actually factor. This will factor into 4x plus 1 times 2x minus 1. Is that indeed the case? Well, here's our 8x squared. This gives us a minus 4x. This gives us a positive 2x, which combines to a minus 2x, and we have a 1. So this right here are our factors. So we can write this up here, if I remember what it is. 4x squared plus 1 times 4x plus 1 times 2x minus 1. So 4x plus 1, 2x minus 1. And then this right here is the factored version of the polynomial. So this is the polynomial in standard form. This right here is the polynomial in factored form. And that is it for this particular example. And here we are back in PowerPoint. And let's move on to our next slide. Okay, the next slide has to deal with the fundamental theorem of algebra. And it pretty much says that every function of degree 1 or more, and what does this mean? Well, this means every function that actually happens to have an x in it, at least an x. It could be an x, x squared, or whatever. It will have at least one complex valued 0, which means there is one value of x where this thing crosses the x-axis. Now, that value of x may not be real. For example, suppose you actually have the function y is equal to x squared plus 1. It's going to look something like this. Does it touch the x-axis here? No, but there is a value of x where this thing actually happens to be 0, and that value is basically I. It's either I or negative I, plus or minus the square root of 1. So there is a value. There is a value where this crosses, although you can't see it on the plane, at least not in the real Cartesian plane. It just turns out that number happens to be purely imaginary. Furthermore, the other important theorem is the number of zeros theorem, and this pretty much says that if you have a function defined by a polynomial of degree n, then that function will have at most n distinct zeros. Now, it turns out that the function will have exactly n zeros, but those zeros may actually be may share a common value. For example, for here, we have 4 zeros, but they're all at the exact same point, so there's only one distinct 0. But it is possible to have as many as n distinct zeros. What you cannot have is, say, n plus 1 distinct zeros. A polynomial of degree n cannot have n plus 1 distinct zeros. So let's take a look at this particular example. Now notice we want to find a polynomial function of degree 3 with real coefficients that satisfies these conditions. -1 is a 0 with multiplicity 2. And based upon our previous discussion, that means one of the factors is going to be x plus 1 raised to this power 2. Okay? And then finally, the other 0 is at 2, which means that the other factor is going to be x minus 2. As a consequence, we know that f of x is going to be equal to some number, let's just go ahead and call it a, times this factor, which is x minus 2, times this factor, which is x plus 1 squared. Okay, well, notice we have a third bit of information. That is, if you evaluate f at x equals 1, you should get -8. Okay, so let's go ahead and do that. F evaluated at 1 is going to be basically this function will replace x with 1, and that will be a times 1 minus 2, which is -1, times 1 plus 1, which is 2, squared, which is 4. And this will be equal to -4a, and that is going to be equal to -8. Okay, solving for a, we have that a is equal to positive 2. And that means that our function is going to be f of x equals to 2 times x minus 2 times x plus 1 squared. And there you go. Boom, we solved example 4. And this brings us to, we're going to skip that one, to the conjugate zeros theorem. And this is what the conjugate zeros theorem says. It says that if f of x defines a polynomial having only real coefficients, this only applies if the coefficients are real, then if this complex value, z a plus bi, whatever that is a 0 of f, then its conjugate is also a 0 of f. And we have actually seen this in quadratic functions. For example, when we have something as trivial as x squared plus 1 is equal to 0. Okay, if we actually solve this, we would find that x is equal to the square root of -1, which is I, and also the negative square root of -1, or minus the square root of -1, which is -I, and these are actually complex conjugates of each other. And that applies for any quadratic equation where the discriminant is negative, and it also applies for any polynomial function where the roots or the coefficients happen to be real. And how do we use this? Well, check this example out. Here we want to find a polynomial of least possible degree with real coefficients that satisfies these conditions. Okay, well, if it's going to have real coefficients, and if it has least degree, we want to have as few zeros as possible. Okay, well, here we have 1 0, that's x minus 4, okay, times something else. We have no idea what that is yet. And it's also going to be a factor of this particular 0. But remember, if 3 minus I is equal to 0 and we have real coefficients, then 3 plus I, its conjugate, must also be a 0. And if that's the case, then f of x is going to be equal to the product of x plus 4, I wrote that wrong, times x minus this 0, 3 minus I, times x minus its conjugate, which would be 3 plus I. Okay, awesome. Now, if you evaluated this on these two factors using FOIL, the FOIL method, you would have that this is equal to x squared minus 6x plus 10, which leads you to now having, which leads us to evaluating the expression f of x is equal to x plus 4 times x squared minus 6x plus 10. Okay, here we're going to multiply x by every single term here, and that would give me x cubed minus 6x squared plus 10x. Okay, then I'm going to multiply 4 by every single term here, and that will give me 4x squared, which I'm going to write under here. And then negative 24x, which I'm going to write under here, so I can add vertically, and then positive 40. Okay, now I can add all this up vertically. I'm going to have x cubed, and then here negative 6 plus 4 is going to be negative x squared, minus 14x plus 40. And this right here is f of x in standard form. And I'm pretty sure that in your homework, when you encounter this type of a problem, which by the way they will want your answer not in factored form, but in standard form. Okay, and here we want to talk a little bit about how polynomials of a certain degree behave. And the first thing I want to mention here is that the polynomial function with real coefficients of odd degree will always have at least one real valued 0. And now keep in mind that if you have a polynomial, say of odd degree, say of degree 3 or degree 5 or degree 7, then they will have 3 zeros or 7 zeros or 5 zeros or 7 zeros respectively. Okay? Now they may be distinct, they may be the same, but there will still be 3, 5, or 7 zeros. Suppose you had a polynomial of degree 3. Okay, they can be, their zeros basically could all be real zeros. So you could have x minus k1 times x minus k2 times x minus k3. Okay, but suppose that one of the zeros was actually complex. If you have, so one of the zeros was x minus a plus bi. Well, if that's the case, then there must be another 0, which is the conjugate of that, which would be x minus a minus bi, which would leave one other 0 left, and that one 0 cannot be complex because there's nothing to pair it with. So that 0 would have to be the function x minus k. Okay, so even if you had degree 5 or degree 7, if you had a collection, you could have as many as 6 complex zeros, because you can never have a 7th complex 0, and you'll always have at least one, and you would always have at least one that is 0. So if you have a polynomial of odd degree, you are guaranteed to have at least one real valued 0. However, if you have a polynomial with real coefficients of even degree, then it is possible for every single 0 to be complex, because each one can be paired, and therefore there would be no room for an additional real valued 0, such as what you would have here. And that brings us to this example. Here we want to find all the zeros of this particular polynomial given the fact that 2 plus I is a 0. Well, if 2 plus I is a 0, then it follows that 2 minus I is also a 0. So therefore we now know two of the 4 possible zeros. We just need to find the other 2. And how are we going to do that? Well, let me bring one note up. There it is. And basically we're just going to divide out, we're going to divide f of x by 2 plus I. and then again by 2 minus I using synthetic division, and then see what we have left. So let's go ahead and do that. Here we're going to have 2 plus I, and we are going to divide 1. Our coefficients are 1, -1, -17, 55, and then -50. I should have given myself more room over here. Draw my line, bring my 1 down, and then 2 plus I times 1 is, well, 2 plus I. -1 plus 2 plus I is 1 plus I. 2 plus I times 1 plus I, if you do the math, you'll find that to be 1 plus 3I. -17 plus 1 plus 3I is going to be -16 plus 3I. 2 plus I times this will be -35 plus minus 10I. 55 minus 35 minus 10I is going to be 20 minus 10I. And then when you do, and then finally this will add to 50, and we have a 0. But most importantly, we have our new quotient. Our new quotient is going to be 0, 1, 2, 3, x cubed times the quantity 1 plus I times x squared times the quantity -16 plus 3I x plus 20 minus 10I. And now we can, and I forgot the plus here, and now x minus the quantity 2 minus I, since it is a factor of f of x, should also be a factor of q of x. So let's go ahead and divide out 2 minus I, x minus 2 minus I from q of x and see what we get. So in our synthetic division, we are going to add this term right here, which is 2 minus I. And then our cubic coefficient is a 1. Our quadratic coefficient is a 1 plus I. Our linear coefficient is a -16 plus 3I. And then our constant coefficient is 20 minus 10I. So even though these are complex values, you can still do this. Okay, draw my line down here and add a 1. Okay, so here I'm going to get 2I, 2 minus I times 1. Well, that is just 2 minus I. Add these together. Fortunately, the i's go away, and we have a 3. Okay, well, then we multiply 2 minus I times 3. That will give us 6 minus 3I. Add those together, and we will have -10. All right, and then finally, 2 minus I times -10 is going to be -20 plus 10I, which of course gives us our 0, which we were hoping for. And this right here are the coefficients for our new quotient, which, by the way, is going to be x squared plus 3x minus 10. And this easily factors into x plus 5 times x minus 2. So then our other zeros are going to be, well, 2. Well, first we have 2 plus 1, or 2 plus I. We have 2 minus I. And then the other two zeros are going to be, well, are going to be x is equal to 2, and then x is equal to -5. And these right here are the 4 zeros for this particular function. Okay, and this brings us to the last thing that we want to talk about, which is the Descartes rule of signs. And this is a little bizarre, but let's just go through it really quick. Let's suppose that f of x is a polynomial function with real coefficients and is written in a non-zero constant term, and is written in basically standard form in terms of decreasing powers of x, which is basically what standard form is. Then the number of positive real zeros of f equals the number of variations in the sign that occurs in the coefficients, or is less than the total number of variations by an even positive integer. So if it's 3, it could be either 3. If it's 5, it could be 5, 3, or 1. Or if it's 2, or if it's 4, it could be 4, 2, or 0. Okay, the number of negative coefficients is pretty much the same number, except when you evaluate f of negative x, then you would count the number of variations in the sign, and then the number of negative real zeros is going to be either going to be equal to the number of variations in the sign when you evaluate f of negative x, or it's going to be less by an even positive integer, 2, 4, 6, 8, or whatever. How does that work in an example? Well, let's check this one right over here. Here's our function. Okay, we want to determine the number of different possible combinations of positive zeros, negative zeros, or complex. Okay, so let's take a look at f of x evaluated right here. We start off with a negative. It goes to positive here, so that's 1. It goes back to negative here, that's 2. It goes back to positive here, that's 3. And that goes back to positive, and that goes back to negative here, so that's 4. So there are there's a possibility of 4 positive zeros, minus 2, there's a possibility of 2 positive zeros, or there could be 0 positive zeros. Now let's go ahead and evaluate this at negative x. If you did, you're going to have negative 2 times negative x to the 4th, plus 3 times negative x cubed, minus 5 times negative x squared, plus 4 times negative x, minus 1. Okay, so here negative x to the 4th is just x to the 4th, so we have negative 2 x to the 4th. Negative x cubed is basically negative 3 times x cubed, because we have an extra negative 1 there. Then we're going to have, this is nothing more than just x squared, so it's negative 5x squared. This will be negative 4x minus 1. So notice here that there are no variations whatsoever in this particular function. So there can be 0 negative roots. Okay, but now keep in mind, this is a polynomial of degree 4, so there are 4 roots. So if they are not positive or if they're not negative, then the other 2 roots must be complex. So with this, we can actually write a table of the total number of possible roots. There, we can have a positive column, a negative column, and a complex column. All right, so we can have as many as 4 positive roots. We can never have any negative roots. Well, if we have 4 we have 4 positive roots, that means that all the roots are positive, and we can have no complex roots. Well, suppose we only had 2 positive roots. Well, we can have 2 positive roots. We cannot have any negative roots. So then the other 2 roots, because there must be 4 roots, they must be complex. Okay, so that means we would have 2 complex roots. Well, it could be possible that there are no positive roots, 0, and then there are no negative roots. And what does that tell you? Well, that tells you that all the roots must be complex. Okay, and that is pretty much how you can apply Descartes' rule of signs. And that is all I have for this particular section. If you have any questions, please feel free to contact me. And this is Bob Boyle signing off.